is Randy or Andrew.
I'm Allie.
And I'm Riley, and this is our Dynamics project, a simple overview of magnetic resonance imaging and spin echo sequences.
Starting off, what is magnetic resonance? Magnetic resonance is essentially the absorption or emission of electromagnetic radiation by electrons or atomic nuclei in response to the application of certain magnetic fields. As you can see here, magnetic resonance imaging, noted as MRI, is based on the principles of nuclear magnetic resonance, NMR, a spectroscopic technique used to obtain microscopic chemical and physical information about molecules. MRI is based on the absorption and emission of energy in the radio frequency RF range of the electromagnetic spectrum. On the left here, you can see an example of an NMR signal, which is then sent to the imaging device to produce the image that we see on the right, known as the MRI image.
Once the nuclei are placed in a magnetic field, they align with the z-axis. Then the MRI machine sends a radio frequency pulse into the body to unalign the nuclei. Next, the nuclei begin to spin in the magnetic field, giving off its own radio frequency signal. The MRI scanner detects these signals to form the imaging. The RF signal produced lasts different amounts of time based on the tissues being scanned. The time it takes for the RF signal to fade is called T2 relaxation. And T2 relaxation can provide tissue contrast in imaging. Lastly, the nuclei realigns with the magnetic field from the MRI machine. This time also changes based on the tissue type and is named T1 relaxation. In short, an MRI machine knocks spinning protons over, detects RF signals produced by them, and waits for them to return to their original position so it can form a useful image. The most important of these elements on the screen, helium, carbon, lithium, boron, and hydrogen, is hydrogen because there's an ample amount of it within the human body. Certain atomic nuclei can absorb and re-emit RF energy when placed in magnetic fields. Hydrogen is the most abundant molecule in the body because the human body is 70% water and each water molecule has 2 hydrogens in it. Water is found in almost every tissue and organ, so working with hydrogen allows the MRI machine to scan almost every tissue in the human body in depth.
A hydrogen nucleus is a single proton with no neutrons. This can also be recognized by looking at the atomic number in the top left of the periodic table of elements. The atomic number of 1 tells that there is 1 proton in the atom. The atomic mass shown on the bottom of the periodic square is the number of protons and neutrons. As you can see here, the atomic mass of hydrogen is 1, meaning there are no neutrons. As shown on the right, there is 1 electron orbiting the nucleus. This spinning charged particle produces a magnetic field called a magnetic moment. Also, because of their positive and negative poles, each proton of a hydrogen atom has the ability to act like a simple bar magnet.
Normally, the protons of hydrogen are randomly oriented, meaning they all face different directions. But when they are subjected to a magnetic field, they all align.
MRI is a giant magnet. The magnetic field strength of an MRI machine is measured in Tesla, and the strength of an MRI machine is between 1.5 to 3 Teslas. An electric magnet of similar strength would be able to pick up a car, so it is extremely powerful. As you can see in the upper part of the screen, there are many different layers and components of an MRI machine, starting with the radio frequency transmitter and receiver, which sends and receives the radio signals, the main magnetic coil, which creates a uniform magnetic field, followed by the magnetic coils in the X, Y, and Z direction.
The magnetic field from the MRI machine aligns all the protons with the z-axis, making them parallel or anti-parallel to the primary magnetic field, B0. This arrangement of protons creates the net magnetization vector.
In magnetic resonance imaging, we harness the intrinsic property of protons known as spin, a quantum mechanical characteristic that measures both angular momentum and magnetic moment. Think of protons as a tiny bar magnet, each with its own unique spin. When placed within a magnetic field, they align themselves like spinning tops as seen in the video. The spin equation, incorporating the spin quantum number, Planck's constant, and the gyromagnetic ratio, represented by gamma in purple, which is a unique number for each specific nucleus. In MRI, the gyromagnetic ratio is fundamental because it governs how quickly protons precess in the strong magnetic field, influencing the resonance frequency and the ability to detect signals used to create images of bodily tissues. In MRI, protons' spin and precession are vital for generating signals used to create detailed tissue images. Precession occurs as hydrogen protons wobble around the magnetic field's direction, with frequency determined by field strength. These signals are crucial for constructing images, aiding in medical diagnosis and treatment planning. The spinning of protons generates a change in magnetic field, which in turn affects the magnetic flux passing through the coils of the MRI machine. This fluctuation in magnetic flux is governed by the precession frequency of the protons, denoted by omega in the equation. Representing the rate at which they wobble in the magnetic field, magnetic flux, defined as the total magnetic field passing through an area, is crucial in MRI as it influences image quality by inducing currents in the body and varying sinusoidally over time with a specific frequency. Lenz's law demonstrates how a change in the magnetic field near a wire induces a voltage or a signal in the wire. This principle is crucial in NMR imaging, where the changing magnetic flux due to spinning protons induces a voltage difference in the coil. This induced voltage serves as the basis for detecting the NMR signal of protons, allowing for the creation of MRI images. Larmor's equation reveals critical insights into proton behavior in MRI. When placed in a magnetic field, B0, protons precess around the axis of the field due to their spin. Notably, a difference in gyromagnetic ratio means protons precess at different frequencies in the same field. Moreover, as the strength of the magnetic field increases, the precession frequency also increases. This results in stronger signals at higher frequencies, enhancing efficiency in signal detection by MRI devices. As you can see in the Desmos graph, it is still represented sinusoidally as the previous Lenz's law. In MRI, externally applied radio frequency pulses manipulate magnetization. These pulses can knock protons down from their equilibrium state in the longitudinal direction into an alternate plane, altering their longitudinal magnetization. The degree of this alteration, known as the flip angle, is determined by the strength and duration of the RF pulse. It's crucial to note that the net magnetization vector, representing the collective alignment of proton spins, undergoes this flip. Additionally, understanding the longitudinal direction as vertical and the transverse direction as horizontal is essential for comprehending MRI principles.
When the RF pulse applies energy, the protons precess together in phase. This brief synchronization is called transverse magnetization. This organization and synchronization caused by the RF pulse is only short term. Eventually, the protons return to the original disorientation in asynchronous precession.
This equation shown symbolizes the signal that the imaging machine actually detects. So where does this equation actually come from? Let's start from right to left. As shown in pink, the rate of change of flux produces voltage. We know this already from Lenz's law. As flux changes more rapidly, the precession frequency increases, and so does voltage amplitude, which means a factor of omega needs to be put in front of the cosine omega time part of the equation. Then, gamma beta is substituted for the omega in front of the cosine term, since omega equals gamma times beta from the Larmor equation. The flip angle is the angle the spin makes with respect to the magnetic field. In this case, the more perpendicular the spin is to the magnetic field, the higher the signal. This is why the spin theta is used. Lastly, there isn't just one spin occurring at a time. In reality, there are billions of spins that actually contribute to the signal. This is why a factor of n is multiplied into the equation, which shows the number of spins contributing to the signal. Spin echo sequence. As previously mentioned, the net magnetization vector is what gets flipped when the RF pulse gets applied. The amount of net magnetization flip depends on the strength and duration of the RF pulse. The four main steps of the spin echo sequence is shown here in the bottom right picture. The protons are showed in a random orientation to start. Then, between step A and B, the magnetic field, shown as B0, causes the protons to line up parallel with B0. This is considered to be the beginning of the spin echo sequence. Step 1 of the actual spin echo sequence is shown as step C in this photo, and it is when a 90-degree pulse is applied to the net magnetization vector, shown as the black arrow labeled M. This becomes perpendicular to the original orientation. This is achieved by eliminating longitudinal magnetization and generating a transverse magnetization vector by synchronizing the precession of the protons. This step is seen highlighted in yellow. Step 2 of the spin echo sequence is known as the recovery stage. In this stage, transverse magnetization decreases and longitudinal magnetization increases, meaning the protons dephase. This process looks like a spiral of the net magnetization vector along the z-axis, as you can see in this graphic created. This process looks like a spiral, as you can see. This spiral and rotation is actually what induces the electric signal by the process known as free induction decay. Free induction decay is the current that is induced by the rotating electric field, which is called the right-hand rule. Of course, it's not the same as the right-hand rule used in dynamics, however, it is still a version of a right-hand rule. Again, this stage is highlighted in yellow.
Since recovery occurs at an exponential rate, the rate of decay is measured with two main checkpoints, which are T1 time and T2 time. As you can see here, T1 time is shown and explained on the left with the use of a graph showing the difference between a signal with a short T1 versus a signal with a long T1. T1 is when 63% of the longitudinal magnetization vector is recovered. T2 time is shown on the right and is when 63% of the transverse magnetization vector has been lost. Both T1 and T2 values are unique to each tissue type, which allows for each tissue type to appear differently on the image. Here we take a deeper look into T2 values. Images can be generated based on T1 or T2 values. T1 weighted MRI enhances the signal of fatty tissue and suppresses the signal of water. This is seen on the far left in the bottom picture. In contrast, T2 weighted MRI images enhances the signal of water. T2 is ideal for visualizing inflammation, edema, and certain lesions, whereas T1 imaging provides more of a crisp image, highlighting the anatomy or the area being pictured. The specifics of the different appearances of sections is explained in the next example.
Here we see 3 different graphs, which are all free induction decay, which is, again, the signal you detect immediately after exciting the spins. First, we see a blue graph. This is the free induction decay graph for a tissue with a short T2. Now let's add in a free induction decay graph for a tissue with a medium T2, shown here in red. Lastly, a high T2 is shown in green. Decaying exponentially, mathematically, the sinusoidal behavior is multiplied by e to the negative t over t2. The t2 shows how quickly the plot decays. Since these signals decay at a different rate, each tissue would deliver a different signal strength, which corresponds to the different brightnesses of a tissue in an MRI image. As you can see here, green provides a strong signal and would appear bright on the image. Then, red would be more gray, and finally blue, whose spins got out of phase with each other very quickly, would appear black. This again is called T2 weighting, since T2 is the parameter which produces the contrast in the photo.
Unfortunately, there are some setbacks to free induction decay, making it not as simple as it may seem. Some of these drawbacks include that this only applies to 90-degree pulses. Another drawback is that the signal decays very, very quickly, so the scanning machine needs to be very fast in order to detect the signal. The dephasing of the protons also occurs at a speed known as T2 star constant.
As mentioned, the protons dephase and decay at an exponential rate. This is seen in the free induction decay graphs shown previously in red, blue, and green. This is because each proton experiences the magnetic field, noted as B0, at a different strength. This means the protons are never truly synchronized, so over time, the difference in precessions add up and leads to an increase in asynchronous. As seen on the bottom left, the T2 is shown in red and the T2 star constant in yellow. And on the bottom right photo, the progressive series is shown with a graph.
The T2 star constant represents the decay time of transverse magnetization affected by various factors, leading to broadening of the NMR spectral peaks, denoted as W. T2 signifies the intrinsic decay time in a homogeneous magnetic field, reflecting how precessing nuclei lose phase coherence and scramble their spin components in the XY plane. The equation T2 star equals to T2 plus delta illustrates their relationship, essential for interpreting MRI data accurately. Delta represents the additional decay time beyond T2. accounting for factors such as magnetic field inhomogeneities and susceptibility effects, contributing to the decay of transverse magnetization and broadening of NMR spectral peaks. T2 star is worsened by deviations in the main magnetic field B0, exacerbating phase dropout and dephasing. To counteract this, a 180-degree refocusing pulse is set in motion, causing protons to reverse direction and restoring coherence among nuclei, therefore mitigating T2 star effects on image quality. So to summarize, the spin echo sequence proton precession synchronizes after the refocusing pulse, generating an echo containing image information. This process, known as spin echo or fast spin echo imaging, manipulates proton phasing and dephasing using radio frequency pulses to produce signals. The steps involve aligning hydrogen atoms with the magnetic field, perturbing them with a pulse to emit a signal, refocusing with a second pulse to realign atoms, and finally detecting the coherent signal to create the images.
Protons are aligned with the magnetic field B0 and are spinning randomly. Then a 90-degree radio frequency pulse is applied, causing the protons to tip over and create a transverse magnetization vector as the protons continue to spin. The protons realign themselves, which produces a new signal by free induction decay. Then a 180-degree pulse sinks protons spinning for a short period of time, which produces an echo that can be read out by the scanner. When the echo is produced, that moment is called TE, which is time to echo. The machine emits many refocusing pulses to capture multiple echoes, which become successively weaker until eventually the pulse dies out completely, and the entire process must be restarted. The time between each sequence is called TR, or time to repetition. As you can see in the graph, the T2 slowly decreases until it eventually reaches 0 and hits the TE mark.
Thank you. We hope you enjoyed our educational video on nuclear magnetic resonance.